All right. So yesterday we were discussing about how all the algebraic relationship between feature vector and target vector will be reduced to a network of these following individual units. And what are those individual units? Manjunath, what is the individual unit? You're the only person.
ಸರ್ ಯಾರು ಜ್ಞಾನಶ್ರೀ ಅಂತ ಇದಾರೆ
ಎಲ್ಲಿದ್ದಾರೆ ಇಲ್ವಲ್ಲ.
ಇದಾರೆ ನೋಡಿ.
I'm in classroom one, I'm only seeing two people.
No, we have three people here. Okay, sir. Okay, no problem. If you require, I can share the screenshot. What I can see from my end.
No, man. I'm talking about the single unit. I'm talking about the single unit together. Each of this, what is this? Each of this.
This is neuron.
It's a neuron, artificial neuron.
Yes,
Okay. And inside this is a linear threshold unit. A linear threshold unit. See, one thing you have to remember is machines can only do 0 and 1 computation.
yes,
This is all it can do. It is our work to reduce the real world problem to a machine intelligence problem. We can take the machine learning, classical machine learning algorithm approach, where we are trying to solve it using regression, by building polynomials, multivariate, OLS regression results, and naive Bayes, decision trees, support vector machines. All these are different interpretations of getting a prediction using a target, using the feature vectors. Only in case of deep learning, the same real world problem is methodically constructed using something called a linear threshold unit. And all we are trying to do is let them decide the algebra. Like, for example, you see this. You remember this? This is data. And when you see a line, a data like this, you automatically try to, your initial hypothesis is, when you look visually, you can tell that this straight line is going to approximate the trend of this pattern, correct? Where this is your independent, this is your dependent. So this x depends on y. That's why you have y is equal to mx plus c. You remember this?
yes, sir. Yes, sir. Yes, sir.
This m is nothing but the gradient, correct?
Yes,
If this same pattern, what you're seeing here, the same pattern, if suppose this did not look like this, and if the same pattern I'm going to draw again here, you understand this, huh? You already know age and salary, you know how the regression happened, okay? So I'm drawing this pattern now. The data itself is going like this. Now, would you rather put one line like this, or will you put another line like this? Which one is more approximate? The blue one?
blue wala looks more approximate.
Yes. Because it is going through too many more number of points are there. So the error is actually the difference between the approximation and the reality. That is error, correct?
Yes.
So think like this: approximation is the red one in this case, and the difference between the black points, which is the reality, there is an error. There's a mean squared error. That's what it's called, mean squared error. But in this case, the blue case, that mean squared error is much more less because it is following the curve. And because you
Yes.
see you have this, see there are one, two, three. Three units like this. Three straight lines have combined. That's why you will see an equation not like this now. You will see an equation which looks like one second change. First change, second change. Okay. You don't need this. First change, second change, and then the straight line. Okay. So you'll have two, you have to accommodate for two changes. One, it was going like this, then there's a sudden change, the first change has been. The second change has been accommodated by this. Right? So these changes are the weights. Now, when you get these weights, here in this case, we are reducing this real world problem to a regression problem. But in this case, in a deep learning problem, we use an artificial neuron where there is a linear threshold unit. This is a fundamental unit where the threshold is every see this is a linear line, correct?
Yes. 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 Yes.
So
Y is equal to mx.
basically what we did when there was a small change, what did we do? We used a
Dy.
combination of this
Yeah. Difference.
difference. A small double weights came up here, correct? What
Yes.
the deep learning people said is we sometimes don't know how many are required, how many, whether M2 is required, M3 is required. We don't know what is the order that is required, one. And the problem here is this is how many dimensions are this data? This is between just X and Y.
Yes.
Between two dimensions, if there is a lot of variations, you get a complex polynomial. But
Yes.
if the variations themselves are too many, I'm sorry, if the dimensions themselves are too many, what if you're trying to predict the salary? Suppose you want to predict the salary based on only age, it is a two-dimensional problem. But if you're trying to predict the salary based on the kind of school attended, how much 10th marks you got, how much PUC marks you got, and what engineering degree you did, what skill certificate, so many, you can keep on adding, right? Everything you will factor in. So what am I increasing? I'm increasing the dimensionality. I'm increasing the dimensions of my problem statement. When this dimension increases, see, I'm now looking at one, then I'm looking at something else here, like this X is suppose age. Then I'm looking at some others, skill level, S, then school, then the degree. So I'm going to be adding a newer and newer M's here. All together should come and predict my salary. So what are these? We are converting each of these units to a linear threshold unit. You're getting the idea now? Difference between machine learning and deep learning. It's almost sort of, if you want to see it, it's the same, but the way it is implemented is very different. You give a lot of freedom to the networks so that it can converge. I mean, this much is enough. This much clarity and this much intuition is enough. I mean, if you want to really go mathematical about it, it takes some time. But a little bit of working intuition is what we call. That working intuition is pretty much, observable when you see this. Correct? Do you want some time to like sort of think? So getting back to this linear threshold unit. So just remember, There is a small unit, the linear threshold unit. The threshold unit is linear. Inside this threshold unit there are no multi dimensions. Okay, it's a single dimension. So use thousands of linear threshold units and let them all come together and decide
Mm-hmm.
the
Mm-hmm.
complex polynomial whose algebraic realization is nothing but learning the pattern of the data that has been presented to it. Making sense?
Yeah, yes, yes. Learning, yes. It's a kind of a learning only.
Yes, it is. It is. You have reduced everything. If they set up the problem, if they set up the algebra, it is learning. Because what this means, when you say y is equal to mx plus c, if it has found, you take age, you take salary, if it finds out the m value and c value, what are these meaning? Because is equal to, you see this is equal to, this is a bold
Yes,
statement, right? I'm saying
yes,
something, you do something to the age
yes,
and it should become equal to salary, it seems.
yes,
So what is that? What has been found out? The weight, which is the gradient, and the constant, which is a shift. So,
yes.
like this, a complex problem will have into thousand linear entities,
Mm-hmm.
where
Mm-hmm.
each
Mm-hmm.
of this is decided by the linear threshold unit.
Okay, 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 sir. Okay, okay.
Now getting
There
some
will
idea?
be a lot of things will be present in the LTU. So once you feed the data, upload the data, that will decide which one is the suits for this sample data.
Lot
So
of
it
things
will
will not be present in the LTU. There will be a lot of LTUs present.
LTU. Okay,
I'll show you. Hold on to the idea that there are into, let's say, 100 or 1,000, depending on how big your problem is.
okay, okay.
Okay, see, if there is only one target vector for which there is only one feature vector,
Feature vector.
this is enough. Okay.
Enough. Yes.
When there are 20 feature vectors and target vectors are around 4, so it's a 20, it's like this. It's like a very complex combination, right? 20
Okay.
feature vectors and 4. Now, which of these feature, if you want to predict this, let's say A, B, C, D, you have 20 variables, which some combination of this leads to B. You getting this? Some other
Yes.
combination here, some other combination here may be leading to D. Which combination leads to what? Who will learn this?
Mm-hmm.
Right? So this equation is too small for a combination like this. So I cannot now anymore depend on algebraic equations. I need a very complex model wherein next time I give a certain pattern of this, or like 20 parameters if I give as input, it should classify and give me, hey, this is based on the past what I've learned, it looks more like a C class.
Mm.
So the input parameters itself is so big. So here, how many input parameters are there in this model? One.
True.
One. See, input parameter is only one. Output is this.
Yeah. Output is two.
If you
Yeah.
give a new age, it will do the multiplication and the addition of this and give the salary. That's what this is doing. But here I'm not giving only one value. No, I'm giving 20 values. Where are you inputting
21.
those 20 values? X1, X2,
1 is to
X3,
X3.
X4. So many are there. Where? How does it look? So this is the complex deep learning model. This complex deep learning model is the one. Huh. So this one, so basic, now you see, now I will see you getting some idea now. You got this idea, right? You're getting some idea now. You'll see that's why I'm repeating it again and again so that once you get the idea, you'll start enjoying it. Now, lot of linear threshold, a layer of LTUs. What is this? A single, this was the first artificial neuron. Then came in that artificial neuron, condition to fire. You see, the condition to fire C was just deciding whether A is getting fired or B is getting fired. That was the first artificial neuron. Second layer, when they evolved and they started thinking, let's build something else, they put more condition where they said, no, now it is not only about whether A is firing or B is firing. Now I want to say how much, at what level A will fire, delta 1, and how much level B will fire, that will decide whether C is going to fire. I'm bringing in this new dimension here that is called the weight. So you can see the same weight realization when you're doing y is equal to mx plus c. This is also the same weight, but this is a simple linear regression problem. But what if, so basically it's like this. What if you can reduce a complex data problem to a 10K linear regression problem? Are you seeing this? Are you now getting the intuition? 10,000 linear regression problems can solve a complex problem for you. Basically, that's what we are doing. Now, this is, I think, this is the way in which you should understand. You know the simple linear regression problem. But what if I can use 10,000 small units where linear regression is taking place inside and they're all connected to each other? Now, after everything is done, we pick up all those, not all 10,000 neurons are going to qualify. There are certain neurons which will be bad deciding, some neurons will have good decisions. So what if you take all the good neurons which decided the right weights and then you build an algebra out of it? That is a new model for a complex data. So, and it's not surprising because you can't do anything else. As I told you before, only a machine can only do zeros and ones. So if this can happen in a machine, what have I done? I have just made this. Now this is happening in, let's say, one iteration. Okay. I just want another 10,000 like this to occur parallelly. Then after that, I will combine everything. So that's why you need a GPU for this, a graphical processing unit, because the dimensions are too many. So you get the idea. Linear threshold unit is the second in evolution of intelligent automata. Now, next comes when you have many layers of LTUs, the first learning, actual learning realization, the first learning machine, which was mathematically proved, mathematically realized, okay, was the perceptron. What is a perceptron? Just some weight, and then what is the activation? At what is the threshold? For a certain weight, this threshold opens up. Okay. So a perceptron can learn by reinforcing weights. It's weight reinforcement. Why am I saying reinforcement? Because this weight is not hard coded. This weight is not the C. C is not the weight. This M is there, no. This keeps changing. So we allow these weights to change so that the target and the feature, it finds a way to match the features to the target by manipulating different weights. It's like saying, um, I'll show you that whole animation so you'll get that idea. And right now I'll show you that animation so you'll get that idea. Anyway, so moving
Sir, I
on.
have one question. I have
Yes,
one
please.
question.
Yes, please.
Yeah, so the threshold will be decided by LTU only. So what threshold it has to be fired, but it is not predefined and it is not hard coded also. That was you mean to say.
Correct. See, now you may have forgotten. That's why it's important to write and think. You may have forgotten, so let me again show you that threshold is nothing but that m value, the
Yeah, yeah,
diameter
got it, got it.
weights.
That's the M value.
So what was that m value here in this data? This one, right?
Yes.
Delta change in x, delta change in y. That's why it is dy by dx. The change in y divided by change in x. But if the data is like this, then the line is like this, no?
Yes.
Then how much if you do this, you see now,
Yeah.
big delta, no? Dy is too much.
Yes.
Means what? For a small change in x,
It will increase us
a
dy.
huge increase in y. That is what this m stands for, the slope.
Okay. Okay. Okay.
Okay, these are all the small slopes.
Oh, 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 oh.
That's why I'm
Oh.
reducing a complex data problem to a 10,000 linear regression problem. Then I know the mechanism to club all that in the end. That's what MLA, that's what deep learning is. The problem is in deep learning, once the model is built, we can't understand, like at least in a linear regression, you can actually see y is equal to mx plus c has
There is
been
a direct
realized.
straightforward.
You can actually see this. Okay.
Yes. Yes. Yes.
But in a deep learning problem, once the model is built, even if you go and see how the model looks, right, you can't make sense of it at all. We don't know how it learned. We don't know what it did, but it learns. That's it. So that's the mystery because it's too complex. See, 10,000 combinations connecting to each. Here only see how many combinations are there. It's a simple perceptron. So we can now see this is one layer now. Okay, one layer. Think of it like a bread slice. Suppose this is one bread slice.
It will be many slices.
So you can now you start thinking that what if you keep on slashing another layer, another layer, another layer
Yeah. Yeah. Yeah.
inside again. So now there is not only connection like this, there is connection like one first floor to second floor, second floor to third floor, third floor to fourth floor.
Okay. 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 Whenever it's required, it will fire. Otherwise, it will not fire.
Correct. If the data is too complex, we can keep on adding newer and newer layers.
Yes. Yes, sir. Yes, sir. Yes, please. Yes.
Okay. Because see, our problem is not a single two-dimensional problem, right? I just told you 20 feature vectors trying to connect to suppose four target vectors. So many combinations are there. Anything can happen. We have to allow them. So I will give you another very beautiful interpretation. Just waiting for that, waiting for me to finish this small intuitive this one. Okay,
To
let
do
me.
this, we require supercomputer, Vijay.
No supercomputer. That's why we require GPUs,
GPU.
graphical
Okay.
processing unit. This graphical processing unit, now CPU is linear. You see the CPU, no? You see the CPU
Yeah.
architecture. You
Control
have an
processing.
ALU, you have an input, output,
RAM.
then control unit, correct?
Yeah.
Together it becomes one processor. It is linear. A simple CPU is a very linearized thing. What if you have uh, 30 CPUs all layered like this? That is a
Mm-hmm.
graphical processing unit. It is there,
Okay.
and they've already who's doing lot of GPUs? Nvidia. That's why you recently saw Nvidia's share price had gone to sky. I mean, it's probably the most
Oh, they are
valuable
producing the
company in the
GPUs.
world. Yeah, they manufacture GPUs for servers, for cloud.
Okay. 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 Oh, it's a chip manufacturing company, artificial intelligence chip manufacturing.
Yeah, processors, high gaming processors. Nvidia gaming. You must have seen everywhere. You see
Yeah.
Nvidia. For games to happen, you needed graphical processors. A processor
Mm-hmm.
which can process graphical, high definition condensed data, correct? Because you see, when you play a game, how many things are happening at a time? You play a car game,
Yeah.
like a car
Yeah.
is
Yes.
moving, your other car, your racing car is moving, something else is being shot at, helicopter is coming from above. At a time, how can you see all this? Your brain is complex. You can perceive everything, you can enjoy this whole world. But a machine, The machine is also doing that now. How?
Yes.
Because they have parallelized this dynamic programming which has been running in parallel. Everything is computing, getting computed parallelly, then getting combined and getting thrown out because of the sheer power of computation today. Supercomputer, yeah, probably in 1948, the present computer would look like supercomputer. But today, a supercomputer's definition is very different. Okay, so see what I told you, perceptron, then a multi-layer
Multi-layer
processor,
processor. Yes, yes, yes.
addition of hidden layers. This addition of hidden layers is your deep neural network. Okay, so
But in the real world, we cannot touch like that, right? Only we can feel.
yeah, it is all we can't touch it because each one of this is just it's not a real thing. It's a small. Imagine this as a
Nano,
small C code.
nano chips, nanos.
And a chip, no, everything is not getting solved in the chip. Your chip is only a complex processing unit, boss. Don't think of this as 10,000 small chips. No,
Okay, 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 okay,
no. There is only one computer. Inside
okay,
this computer, I am creating small C programming code, small C code.
okay, okay, okay,
Another
okay,
small. See, if I create one C code, I can make
okay.
10,000 small codes out of this. No, same, repeat, copy
Yeah,
paste, copy paste.
multiplications.
Yeah.
Yeah, multiplications.
But when I copy paste, I copy pasted. Then I connected everybody. I just said, okay, each one if you talk to each other, no problem.
Yes.
But then I say, don't simply talk and chit chat anything you want. You only discuss about the feature vectors I'm giving you and try to
And decide
connect
the
it to
target
the
vector.
target vector. Now you
Yes, sir. Yes.
discuss between each other. The discussion's result is the weights it is giving. So finally, you have a lot of weights that is going to come here. Weights and the threshold values.
So how do you decide this functions actually? Like for a given task, how many such needs to be spawned actually? Such functions needs to be.
Very good question. There is, we'll come to that. Okay, you'll eventually get to a fair idea. It will little deeper. Okay, you will get to see how many features are there, how many how many. I'll show you now. You will do that exercise now. I think I have it open somewhere. Maybe. How do you decide his?
One more question, Vijay. So actually, in modern cloud computing, there are various uh, streaming tools available. For example, Storm is one of the tool. Link is another tool. Do we use such kind of a thing for distributing the load across the functions?
No,
Basically,
inside this distribution, inside it is something else is used. This is not that distribution. That Storm is only Storm and Apache, Spark and Storm. Storm is for real time, Spark is for parallelization of the
yes, yes.
computation itself. Okay,
So
internally,
basically, there is a soft and bolt concept, right? So that's what I was thinking because you are basically the load is getting distributed. It's load balanced across various functions. That's what I understood. So
in the cloud computing, you're saying.
no, no, I'm asking, will it use some kind of such infra tools, or will it be just
Are you saying whether deep learning is used in cloud computing architecture, or are you saying whether cloud computing architecture is used inside deep learning? Which one are you asking?
even learning is reusing the cloud infra or cloud computing technology?
I don't know. I don't know. Maybe in future, maybe if the computers they develop it at that level, maybe in future, because you need multi-layered models itself. That here it is one for one model. To get one
Mhm.
model, you have multi-layer perceptrons.
Okay,
What if
okay, okay.
tomorrow, if you want to really solve a very complex problem, you may need a multi-layer model where you have hundreds of
Understand.
models
Yeah.
working together, and each model is probably hosted on different virtual computers. So if you want to connect all of them, it's possible. It's a good. possibility.
I think yes, for his question, Vijay, I think yes, because after learning this particular logic, that who will decide the threshold?
Uh-huh.
Yeah, if you come to the cloud computing, we have a auto scaling, so that will decide itself. If the RAM breaches, it will add the RAM by itself in auto scaling. If the instance goes down, it will do the auto scaling. It will, if the hard disk space is less, it will decide the, it will increase the volume. So I think we can relate those things to this particular logic. We
Nice.
are, there is no human interaction there. So the system itself decide how much RAM I need to increase, how much space I need to increase, how much instance I need to increase.
Yeah.
So means that is a threshold breach, fire breach. So that will increases the RAM. So maybe we can relate. I think yes, maybe. I'm not sure, but yes.
Maybe. Nice. I'm also not sure. See, I don't say I'm complete. I've gone
That's fine. That's
completely
fine.
into this line.
Just to discover if that is the one. It is
I
okay,
can
but
ask.
that's fine.
I can ask some people who are like. Yeah, I'll get that information. Let me get that. So okay,
It's a very interesting, Vijay. It's very interesting.
this one, right? This is the
Yeah, it's
future,
very
man. This is
interesting.
the present. This is the present. I mean, this is magic. The For me, it's like really magic the
Yeah,
way they've done it. Now, the modern deep neural network, this activation function was there. No, I kept on saying this one, this function, a linear threshold unit, this linearity, right? If it is zero, you be here. If it is one, you come here. That's what it is deciding. It's a small zero one decider. Zero or one, zero or one. But in life, everything is not zero or one. It is gray. Something is dark gray, something is light gray, some is light pinkish gray, something, right? In image
yes.
also, in image processing also. Not everything is black and white. Black and white is easy to identify. So, in a modern deep learning network, this internal activation function, whatever is there here, we use different kind of functions. Okay, different kinds of functions whose only work is a very simple functions, or these are all very simple functions whose only work is deciding should I fire or not. But to decide that, sometimes I want to go, I can't always go like this. Zero, no. One, no. It can't happen. Sometimes I want to go like this. Sometimes I really want to go like this. Sometimes I want to move slowly like this. So all these changes comes with the difference in functions. These function differences are the activation functions. Okay. So we will see that now. We will see those activation functions. All of you, both of you now, go and open this. Okay. Wait, I'll show you the rest here only. Playground.tensorflow.org. Go here. Just open up and try to play around with something. I'll just be back in. I'll just take a washroom break and just be back. But you have to go here. You have to go here and try to do something with this. Just mess around. Okay. Just see. Let's see how you can. Let's see what you can understand from this. Then I'll just be back. You see what I'm saying? Sometimes you'll have to see this whole stuff, as a tensor, because it is managing so many things. It is allowing the network to do so many things. Now, I will give you an interpretation which is going to be very different. You guys are there, ready to listen to this? This is exactly what happens, and this is probably the most realistic, intuitive story that you can, if you understand this properly, no, you have understood deep learning. Okay? Are you ready, both of you?
So what are this noise and these other factor batch size? I do understand. What is noise and
You are increasing the noise. See, when you increase, what is happening here? When you, okay. this noise, do you see any misclassification here? Correctly, you can see here that this circle has all the blue ones.
Mm. Yeah.
This circle has all the orange ones.
Yeah.
So if the machine can somehow create a function to map this region, then it has understood the classification. Next time, everything that comes here, it will automatically give us orange. And everything
Mm.
which comes here, it will automatically give us. So you are training, no? This is training data. You are
Mm.
showing this boss, see, this is the data. Can you identify next time if I give you a data point? Means how? So it's a good question. How? What is this? Do you think the machine is seeing this? You are seeing this. What is the machine seeing? The machine is seeing only this. This point. What is this point on the grid? This point is
Mm.
something like 4.5 and 1.75. So 1.75 comma 4.5 is one location, correct? In this grid,
Mm. Mm. Mm.
this has been equated to orange. Next one, something, let's say 0 here, and this one is around 4.5. Okay, some 4.6 comma 0, also orange. This is the
Mm.
data which goes in actually in a data set. This is only visualization for you.
Yeah.
Okay.
So if
Uh,
noise increases, this this.
Misclassification is increasing. You can see there. If I increase the noise, you see in place of now what happened? You see this? You see this?
Yeah, orange came in.
Came in noise, correct?
Mm. Mm.
Too much noise.
Mm.
In place of orange, there is. This is how data has, right? Not everything is.
Mm.
This was supposed to be. This was supposed to be orange, correct?
Mm.
This blue color
Right.
was supposed to be orange, correct? No, but
Right.
somebody has tagged it as blue, human error, machine error, recording error, observation error. So many errors can happen, right, when you're collecting data.
Mhm.
This is called noise.
Mm. So this noise is nothing but error injected to it
Yeah, we
to
are
find out.
actually injecting the error. So you can see if there is more noise, then we'll
Mm.
have to increase the hidden layer so that it can clearly identify. And sometimes it will take too much time to eventually understand that these are all misclassifications. It will happen if you increase this noise like this, the misclassifications will happen. This noise you are supposed to remove,
Mm.
correct? Because
Right.
when you see this data pattern here and suddenly one blue here, you should remove this. This is outlier here. For
Mm.
this data set is an outlier, and here you see so much. It's just got spread like crazy. This is going to be difficult for the model to identify. Let me not get this batch size and all. I'll tell you later. Okay. This one, when we see the program, we will understand how many. For now, I'll
Yeah.
just keep it as 0. Let's just keep it as 0. And I'm going to remove this. Manju, you understood? Visual and the quantified realization, which the machine will see, and the visual realization for our intuition building. Both are there. You have to understand both. Okay?
Okay. Sir,
Manju, you
can
are
you play
there?
that? Yeah, I'm there.
Play.
Can you play that?
Yeah, I'll play. Wait. We'll play. Just adding a little more. I can play. Yeah.
Yeah.
This is
This is
the.
what I tried.
Yeah. This means clearly the model is able to identify between what is the orange part and what is the blue part. Okay.
Yes.
Now I'll change the data set. You see, I'm changing the data set to this. This is another
Okay.
problem. This is another problem. This is another problem. Try solving this. It's trying hard,
Yeah. Uh,
but But no matter how many seconds, how many iterations it is trying, means it's all it's see, it is trying to connect everywhere. This, you see this animation which is going on. It's trying to give
Yes,
different interpretations.
but it is not
It's not.
exactly.
It's not coming. It's not happening.
Yeah.
Which means these, whatever linear thresholds that you have given, this is a much more complex problem to model
Yes.
than the order. You remember in polynomial regression, you were giving that order, n order, in x comma y comma, you were deciding that 3 or 4 or 5, you're deciding.
Mm.
Remember this in polynomial equation, polynomial regression. You don't remember? When the data is like this and you want this to be the model, then
Yeah.
you have to give 3, no? At least then only you are giving 3 degrees of freedom.
Mhm.
Forgot?
Yeah. Fit to curve.
Curve fitting. Because there is too much variation in the data, you are giving this 1, 2, 3, 4. So degrees of freedom at least 3. You can't overfit it, but at least 3 degrees of freedom. That's why you give x, comma y, comma 3. So it will fit like this. This 3 here is how much degrees of freedom you are giving. So this also you need to increase, and maybe even this layers. So as I told you, hidden
Mm.
layer, keep on increasing hidden layer. So you get for this problem, no, to solve this problem, you need more. And also when this problem, now I'll show you a different interpretation. See, this is the feature, this is the target. Hmm? Feature, target. What a deep learning network is actually a gambling network. Imagine all of these people are gamblers. Understanding what I'm saying? You know what a gambler does?
It's keep on changing.
No, yeah, what does a gambler do?
Bet. He will do a bet on something.
Right.
Correct. Betting. Everybody is trying to bet. Okay. Now, these gamblers here, these gamblers here are closest to the, they are the ones who are seeing this, actually, the real data. Okay. These gamblers. And these are the, this is the place where the guess starts. So when you increase the features, so feature is now like this. For the given data, initial hypothesis is this. This is the given data. Okay, correct. This is the given data.
Mm.
In linear regression, also what we used to do, this is how the model was building. Suppose this is your given data, but you are slowly trying to increase this, no, line. Correct, no?
Mm.
Simply, what do you think? It's like automatically the computer will see this and put a line like this. Not possible. That is a computer, not human being. It will start from here. Then slowly it will increase the m value. Then it will stop here. And then it will compute the distance between points and this proposed model. Then again it will increase the m value. Then again it will compute. The second one it will compare now. Whether in the previous time the distance was high or now it is high. So it will previous was high. So it means it will understand that I have come closer to my data points. So now again let me increase. So if this is the value m1, m2, m3, if this m value, this unit value is too big, suppose you start like this and suddenly you give such a big m where it comes here, then you give another big m because you can't change this, so it will just come off here. So it has missed the real data only. So this is called the learning rate. And this one is the initial hypothesis. The initial hypothesis where I started from here, that initial hypothesis in this case, here in this case, is when you see this data, this was the hypothesis saying, hey, everything on the left could be orange, everything on the right could be
Blue.
one hypothesis. Second hypothesis, everything on the bottom, below the quadrant is orange, everything above the quadrant is blue. Some other, now this is a new variation I've added. I've added a new variation now. I've added a new variation now. I've added a new variation now. A newer variation. I have so many interpretations. These people will decide who is more. Now, looking at, see, all of these are connected. You see, each and everything, this one, all these are connected to this. Then all these are also connected to this. So now what happens? This is the initial gamble we start from. And then we ask all the remaining gamblers to start gambling, saying, you take a guess from this, from whatever all these interpretations are here. No, you look at all, because this one doesn't know this. See, these are all independent people. This gambler cannot listen to this gambler cannot listen to this gambler. But whatever all these people are saying, this one can listen. This person is saying, hey, left is orange, right is blue. This one is saying up is orange, down is orange, up is blue. Everybody is saying something. But this person will listen to all of them and create their own guess. This person will create their own guess. This person will create their own guess, their own guess, their own guess. Again, listening to all of them, this person will put his own guess. You're understanding how
Yes.
this, now
And
finally
that's
this,
it.
now the finally this guess will reach here. Okay, huh? You see, now the story is even more interesting. Finally, after all this guesswork, right, this will reach here. Suppose when it reaches here, this one is actually seeing the data, no? So what it says is, it will say, boss, you are, it won't say it is exactly, it will say, you are about 25% right, it will say. Because it has said, if you see here, it is upper one is orange, it has shown, right? So it's okay, 25% right you are. Now, this one knows exactly whom it listened to more, because it has listened to somebody more. So it will say, boss, you gave me wrong. This one is completely wrong, right? So it say you are completely wrong. And it will say, I listened to you and you, so you guys are right. So I'm going to add some reward for you. That is the weight. Then this person will get the reward. No, it will again say, okay, it will also say, you are about, because it has listened to both of them and got 25% right, right? So out of which, how much percentage both of them got right? 25%, all of them together contributed to this 25. It has reduced the weight. So let's say it is saying, you are 12% right, you are 12% right. Now it is going to go and tell this person that because of you, I took a good decision, but because of you, I could have gone higher, but because of you, took a wrong decision. Again, it is going to propagate back another 6% here. This is also will give some other 6% here. So what you are seeing is back propagation, correct? Feedback
This
network it is.
this reward is also called reinforcement, or what this reward
Change of the
purpose?
reward is reinforcement. Reward is called the weights.
Okay.
That is why it's a good question, yeah, good observation. That's
Mhm.
why in this, see, a perceptron can learn by reinforcing weights. This is what you were answering. This is what you were asking. So that's why now
Yeah.
you're see now you're connecting the intuition to the technical words. That is a good sign. Anyways, now this is called the back propagation, gentlemen. And whatever you're saying, no, this 12% here, 25% here, what I'm giving you a very realistic view of exactly what is happening. I'll show you now. You'll start seeing that now. What this one is actually you're sending back the small delta changes, the small dy by dx's. Okay, when you have many dy by dx, it's called a differential equation, and this differential equation is it's changing constantly. And for this they use a trick, a computational trick to compute this differential equation. It is called auto diff. You can google this. This is a very intelligent numerical method to realize differentiation of high dimensions or differential equations of high dimension. These are all differentials only, right? How much you are different, how much you are different. That's what a differential equation is, isn't it? Differential equation is not only set up in aircraft modeling or anything. Everywhere where you're trying to where you're trying to model differences, a differential equation has to be used. So this is a difference that is being modeled, a gambling difference, a guess difference. So a differential equation gets initialized, and that every time it starts a new iteration, every time it starts a new iteration, again it brings back guess changes. Good people are rewarded, bad people are removed from the network. So you see now, when I load this, of course, maybe this is not enough, but let's see. I mean, I don't remember exactly how many it takes, but I'm pretty sure the activation function for tanh won't be realized. ReLU will probably realize. Okay, ReLU, tanh, these are all the different. This is linear, the linear threshold unit. Then there is sigmoid function. Then there is a tanh function. Then there is a ReLU function. You go there and check these equations. You will understand. Now let me play. You observe this. I want you guys to observe this when it is moving. You see this? It is getting darker. Some are getting lighter. Some are getting darker. Can you observe this?
Yeah, that's good.
That is the weight. This is completely saying you are absolutely wrong. Nobody should listen to them. When this weight is transferred here, no, this person said, hey, you are absolutely wrong, man. So it is heard by everyone. Next time it won't listen to that person because it has learned, right, from each other. I took this guy's decision, this guy's gamble, but it paid off. It completely shifted me off. Because see this, what it is saying. The reality is outside is orange, inside is blue, correct? But what is this saying? Outside is blue and inside is orange. That's what it is saying, right? Gentlemen, speak, correct or not?
Yeah, okay.
Right? So it has to be given negative weight. So it is slowly decreasing its weight on this. And whichever is giving good interpretation, where suppose outside this is orange, okay, this one white means orange, it can't just show everything. So the outside this is blue, so this is getting higher weights. You see, this is a 1.1 weight. It says when I take a gamble listening to this gambler, I'm getting. So you see, everything is gamble. It is just a so the more gamblers you add, of course this has not converged yet, because not enough gamblers are there to gamble. Now I want to tell you something. See, suppose you have a box. Inside that there are four marbles. Okay, you are standing here. Your life depends on somebody guessing how many marbles are here. So if there is only one person, the probability of him getting it right is 25%, correct? Because once he may say one, or maybe he can guess two, maybe he can guess three, or maybe he can guess four, or you don't know, you can guess five, six, seven. Yeah, you will never know, because you will never know what is the probability of success, because he himself does not know how many marbles are here. And you ask them, guess how many marbles are here. If you are right, then this person will live. In this case, don't you think it is better to have many gamblers where at least you are sure? Now, what you're saying is, if at least one of them gets it right, then you are saved. Which one would you like? One person gambling or four-person gambling for you?
Higher is better.
Higher is better, correct? Because at least one person getting it right increases the probability. But
Yeah.
everybody is gambling only, huh? You are just depending on luck here. The luck may favor that this person may decide to choose four and you get saved. Okay. So that, but we are trying to, but if you are trying to give him a hint, you're trying to give him a hint that it is between 1 and 10 or it is between 1 and 5. That is your initial feature engineering. So setting up the features, then setting up the hidden layer, then showing the exact target. This is learning. It is all gambling work actually. Everybody is a gambler here. Making some sense? Visually, at least now you're able to. Later we'll learn learning rate, you understood activation point. Later we'll learn all this. This type is problem type is, you want some other regression problem, it is a regression problem. Okay? You want classification problem, we have classification. So you can go and check
Yes.
and add different. I've already shown you ReLU is one of the very fine activation functions, and it's a little different here. I mean, I'll give you the books. You have to sort of develop some kind of mathematical intuition to actually see the mathematical aspect of this. But you will get there. This is the first time you're learning this. Not the first time for me. It's been a long time I'm learning this. So every day reading, learning, we have evolved to a different. You will also come there, but I'm helping you. It took me a long time to realize the gambler's perspective. Okay, I've never written about it or done anything, but this is something which I want to explore and make it a gambler's network. It is a gambling network. That is, I'm absolutely sure. Imagine a lot of gamblers sitting, okay, and guessing this. In fact, I in one of the colleges, I actually made them play this game. I made a lot of people sit layer by layer in the classroom. Then I showed them. It was fantastic. They learned deep learning in just, I think, 3, 4 hours. It was a small workshop. And they understood the idea of, "Achha, this is how it happens. There is no other way it can happen. There is no other way learning can happen. It is not magic, it is luck. Only you are trying to increase the luck by increasing the number of, okay, only six are allowed. But in reality, you can have many, okay? If you do this, no, it will converge faster. You see this epoch time here, 29, 43, 50, about 100. It will get there faster. In fact, there is an actual setting, exact setting, where you can try around this. Now that's your assignment for today. I'll close it now. That's your assignment. You tell me exactly how many layers. This comes exactly, huh? If you really do it right, it will actually it will actually model it beautifully well. So you have to go and check whether you want to increase the layers or the depth of the layer, or regularization you want to change to L1, L2, regularization rate you want to change, do some changes here. Don't change it much, okay? Don't change this. 0.03, let it be. Okay, maybe you can even decrease this. Maybe it is miss hitting here, so maybe you can decrease this. And this is fine. You just don't touch this. You can play around with this. This is already set. Don't play around with this. This is the best one. You play around with this, play around with this, and do something. But show me, just play around. You'll understand. Okay. Then later tomorrow we will see the other aspects of it. We'll start getting to the technology implementation of these things in real world problems. All right. I'll call it a day, guys.
Absolutely.
Take care. Bye.
Thanks. Thanks.
Bye. Bye.